All right, hello everyone. My name is Amanda Hinchman-Dominguez. I am a Kotlin GDE. I currently work at Groupon. And this is Memory Leaks, Performance Considerations, and Android Cookbook. Okay. Huge thanks to O'Reilly for letting me do this. Writing with them has been a really good experience. It's been awesome to be able to make content around this book. They were just super chill about it, and it's great because I can talk about anything in between the lines of the book. Actually, this talk talks about things in between the lines of the book. Also, there are some things taken directly from the book, and even some things that we took out of the book. So, you know, it's a lot of fun to kind of come back around and be able to focus on the things I like to focus on. So, this talk is loosely based on programming Kotlin in Android, achieving structured concurrency with coroutines. There are only 2 sections on memory leaks in the book itself, but we talk about memory leaks because using proficient concurrency in Android leads to better performance in your application. This is why we have made Kotlin concurrency in Android the primary focus of the book. To better understand memory leaks, one must have a deep understanding of the Android OS, its components and their life cycles, and how those life cycles interact with various data threading primitives. After solving so many, I've been able to boil down some memory leaks that are pretty easy to catch, and they offer major performance boosts. Okay, how many people have profiled their application? Okay, so we have a pretty experienced group today. That's always helpful. I really enjoy kind of like checking with the audience on where we're at on that sort of thing. It helps me gear my talks appropriately. So for those who might not be as well versed with like profiling their application, don't worry, we'll just kind of do a quick starting from the basics. So what are memory leaks? Well, memory leaks occurs when the heap holds to allocated memory longer than necessary. Also, when the object is allocated in memory, but is unreachable for the running program. And memory leaks can be found in your own code, it can be found in third-party code, and it can be found in framework code. One of the perks of a self-managed memory environment is that we don't really need to worry about managing memory ourselves. It's because it's able to destroy the objects that it creates over time. However, this doesn't mean that overhead doesn't happen. In particular, Android sets a hard limit on memory for each app, and when that threshold is reached, the user or the application will usually crash. There's going to be an out-of-memory leak. Also, jank can occur if one is not careful with the kind of objects a device holds in the heap. The point is, memory leaks are everywhere. They're in your applications, they're in your IDEs, they're in your phones, and we're going to keep creating them, we're going to keep finding them and fixing them, and the circle goes on. Okay, why do memory leaks matter? Let's talk about Android and iOS for a moment. Android holds the majority of the global market for smartphone users, and this is no accident. iOS and Android has become very, very close in terms of software for competition, and in many ways, there are many comparable features in Android that simply run better. We do know that iOS continues to reign supreme in hardware. However, this is not necessarily a weakness for Android. Rather, it's a very specific design choice. Android's resources are limited so that devices are cheaper to make and it's more accessible to the rest of the world. And this is why Android needs to take on a more conservative view of being able to manage memory. So while it's true that you do see less memory-related issues on newer devices, it's still important to ensure that your application is accessible to the majority of the users in the world, especially those who might have older devices. So when I first started learning about memory leaks, I learned that I had personally put in a few myself, and it can be kind of shocking and humbling to learn what memory leaks you've put in your own code base, but I think it kind of helps to know that memory leaks in general is kind of like not a huge conversation it just kind of existed in the background at best. But now, we're airing out the skeletons, and there's going to be no shame, especially knowing that it's not a huge conversation, especially like an Android upbringing. I mean, I really didn't start looking into memory leaks until I was like managing things by myself. I'm like, why did I wait this long to find out about this? Oh my gosh. So, like I said, we're going to keep finding these new memory leaks, we're going to keep creating new ones, and we're going to keep fixing them. So we can't catch all of them. But I've compiled a list of quick and easy fixes with pretty large payoffs. Low-hanging fruit, if you will. Where did it go? Okay. This is a scorecard of the first section of quick fixes. Android components and clashing life cycles. Don't worry, I'll leave that long enough for people to actually take pictures. So Android is made up of a library of running components. Android application components each have a life cycle of their own, which is created, managed, and destroyed by the Android operating system, not by user code. So this is what makes the Android OS unique to how other operating systems work, and also what makes memory leaks in Android so special. Right, so here's our quick scorecard, and don't worry, we're going to go over each of these individually. Okay, first one. Statically saved Android components, remove them. So statically saved references are stored permanently in the JVM. They're never garbage collected throughout the lifetime of the application, and as a result, you want to avoid accidentally saving Android view context fragment activity. So avoid using the static keyword in Java and then saving it as like a member variable, or like saving it as a member variable within a companion object in Kotlin. So the reason for this is because a view in Android has an implicit reference to the activity it is associated with via get context, and is able to reference its own children as well. So if any objects happen to hold a reference to an activity, its context, or any of its views when it's destroyed, then the activity leaks along with the entire view tree. Really big leaks. So remove those static references to UI components. Remove them. Okay, actually, let's go back just for a second. So we can see in here, like, there's a context saved within a companion object, and of course, like, the policy is just to remove. So, okay, number 2, Android UI interactions within non-Android classes. This one is not like necessarily a hard line, but I would say as like a general guidance, like if you have UI interaction, it's probably better to move any kind of UI interaction to the UI level, the UI layer. Developers commonly inject Android components within non-component classes. I'm not saying it's wrong. However, this also requires developers to attempt to manage an Android component lifecycle themselves. It's not that it's impossible to do. It's more like it's crazy difficult to account for all possible cases. And this includes Android Jetpack components like navigation and composables views as well. So keep Android components and interactions only within Android component classes. This way, having to handle lifecycle considerations is not part of your work as well. So one common mistake I see in a lot of code bases, never inject an activity or fragment or its context directly into your presenter class. I know this is something that can be seen usually with like more junior developers, but like I said, there are like some sneaky ones that kind of come in that maybe we don't think about as like Android UI components as much. So the next slide is the fix. Using an interface to tie to the related activity and fragment is how we can send a callback to update the UI while keeping the responsibility of the UI interaction within the activity and fragment. Okay, so in this, you can see that we actually pulled out the interaction into an interface, and we call that interface instead. Okay. Right, and now that we're back in the presenter class, you'll see that we have like the view.onTile loading success, and we're injecting an interface instead of just a straight activity in there. So now we're calling the onTile loading success in the presenter. The business logic is intended to hold state even after the activity itself dies, but just the state. Okay, third one. This one's kind of interesting. Listeners and view members in fragments. Nullify them. You want to nullify them on destroy view. So this one, remember how I mentioned in the beginning of the talk, the definition of a memory leak is kind of debatable. This is one of them. This was actually kind of like an argument between PY and Google, and then you'll see down here there's like that issue where that's like the actual reference to the conversation. Yeah, so like I said, you want to be wary of third-party libraries that may reference the use of Android resources. If you're thinking of adopting a third-party SDK, definitely, like, if you have the ability to check the code, definitely check for that stuff. But here's the big thing. So the fragment's view, but not the fragment itself, is destroyed when a fragment is put on the backstack. I'm sure they put this in documentation now, but at the time they didn't have it in documentation, and then they just expected all of us to kind of like know about this. So you'll see here, this is kind of a reference to that conversation that we were talking about. And you'll see that it says in the issue tracker that they're not going to fix it. This works as intended. And so like Google's reasoning for this is like, well, it eventually gets cleared out from memory once the fragment is destroyed. However, if you work on a scalable application, and your application's already large as is, that time might matter if you have a really large application. So I can say with large applications, like clearing out these references on destroy has made like a huge difference for the applications I've worked on. So like I said, it's a little debatable on what people consider memory leaks, but I like to take a conservative definition of it, and so does PY, and so does my co-writer. So yeah, you just gotta have your convictions. So, and of course, if you have like a smaller application, maybe it doesn't matter as much. Yeah, I mean, I think that, if there's anything you can do, like if there's any kind of memory leaks you can fix on the go, that's great. But some of these considerations are especially important for scalable applications. Okay, so now we have kind of an example of what we're talking about now. So there's like a map fragment. We're using like map views, position markers. So this actually comes from like the Google Maps API or something. But the thing is, these are Android UI components. And you'll see that we have the onDestroy view. I'm sure in the regular code, if we're not having anything in the onDestroy view, it's probably not going to be there. So map view and position marker objects are held as member references, and they're not going to be immediately cleared on the backstack when the fragment view itself is destroyed. So what you want to do is make sure that you call the appropriate things. So of course you nullify your view references, and I think in this case there was like a destroy for the map view because it was part of the API. So this is what you want to do for your fragments. Remember to do it. Okay, number 4. Did we skip anything? Sorry. Nope. No, I guess not. Okay, number 4, playing with bitmaps. I like to say reduce, reuse, recycle. Displaying large amounts of bitmap data in your application makes it easier to run into out-of-memory errors. When we think about out-of-memory errors, like sometimes, those things come up, but it ends up being more of like a symptom than a cause. And bitmaps are really, really big. So, one way I'd like to look at it is like, you have a full cup and it's just constantly spilling over. So reduce, reuse, recycle. So use the recycle method. Make use of the bitmap recycle to reclaim memory when a bitmap is no longer being used. The recycle method will allow the app to reclaim the memory as soon as possible. Load a scaled down version of your bitmap. Like it's not worth like blowing up a giant bitmap for like little Avi. So use your best judgment. And of course, you can use create scaled bitmap or make use of glide effectively to load those bitmaps. And of course, caching is always a good practice. In order to avoid loading bitmaps again and again from network, make sure to use memory and disk cache. You can use skip memory cache to make use of the disk cache instead of memory cache. And avoid drawing a large number of bitmaps and markers at one time if it is not required. Okay, so we've gone through a whole lot of items regarding clashing life cycles, kind of a little bit of a crash course. Now that we've graduated from that, we're now going to look into memory leaks that come from clashing life cycles with threading. Here's our quick scorecard. Working with threads is already really complex as is and requires an understanding of thread safety rules. So a thread has a life cycle of its own that is separate from the life cycles of those different Android components. So the way that I like to think about it, a thread is very dumb. It starts, it does some work, and when that work is done, then it dies. If that work doesn't finish or cancel, then the thread will never die. So here's a quick scorecard of the possible sources of concurrent memory leaks that are pretty easy to catch and what to do with them. So let's start with number 5, Android UI references to background threading. Okay, suppose a worker thread is created which holds a reference to some activity in a background thread shortly after the activity itself is created. In Android memory management, every thread is represented by regions in the heap. No one region can access another object within another region. So when a user is on an application and rotates the device, the activity is destroyed. The worker thread is created from the activity and will continue to run until that work is complete. Unfortunately, the work never completes thanks to the newly unreachable reference from the previous instance of the activity that died. So garbage collection might not be able to dispose of the dead activity reference, and worse. When the thread finishes, it tries to update the activity with nothing to update, leading to an app crash. Android UI components are not thread safe. It's possible to kill an activity, but this does not necessarily kill a background thread. And because of this volatile complexity, memory leaks are possible as any instances of a component can easily turn into dead weight. So how are we supposed to update the UI from threaded work? The trick here is to force the top-level activity or fragment to be the sole system responsible for updating the objects. You kind of see like a similar theme we got going here. So it's the developer's responsibility to make sure that the heavy work is sent to a background thread, and if the UI must be updated, then the results are returned to the main thread before updating the UI. Okay, remember how static references never garbage collects? Avoid saving data threading primitives statically as well. This is something that I think people don't think about a lot. In this particular example, this is a thread pool executor. Thread pool executors are massive. They have their own thread pools, and holding it statically is just going to take up a whole lot of memory in your application. Just don't do it. Pretty straightforward. Okay, number 7, non-static inner classes within views and activities. Remove them. An inner class holds an implicit reference to the enclosing class until the object itself is destroyed. This is a tricky and common source of memory leaks, especially around threading. If the instance of the tile image view is destroyed, then an implicit reference will be held hostage by whatever thread has been keeping tile image loaded callback alive. Okay, but marking an inner class with a static keyword can be a solution. That will solve the issue, given that the static class may not reference the containing class members without an explicit reference and is considered a top-level declaration. The issue can also be fixed by passing a custom listener pattern. So now, we're passing a listener to trigger the onSuccess call, which is now implemented in its parent class. And when onSucceed starts a new thread, it's no longer holding an implicit reference to the parent class. In this case, the map tile activity. Okay, how are we doing so far? We're doing all right? Okay, love it, love it, love it. Okay, so we have kind of a fun miscellaneous section. I just called it performance considerations. We talk a little bit about context and a little bit about view hierarchy. Okay, so activity context versus application context. Activity context, I like to think about it, it's a UI context retrieved within the scope of an activity or fragment context. You want to use it for accessing UI-related components, inflating views, and showing dialogues. Application context refers to the global application context and is best used for accessing shared resources in the Android OS, shared preferences, URIs, and so on and so forth. Okay, and now, let's see, why, this feels like it's a little out of order, but that's quite all right. Okay, so, wow, that is just, okay. Well, we're just gonna go in this order because that really threw me off. All right, we're gonna talk about view hierarchies really quick. Something that's really important is if you're using the current view system for Android, make it as flat as possible. Use constraint layout. If you have these sitting in your code right now, please replace them. I'll explain why. It's, of course, compose is probably the best option, but you know, we live in a bureaucratic society where not everyone's just going to switch over to compose. Understandable. So until then, we got time. There's going to be time. We're all going to go. So anyway, some older layout types in Android are prone to double taxation when relative positioning is enabled. So with relative layout, without fail, this always traverses its child elements at least twice. Once for layout calculations, and I think another to finalize positioning. For linear layouts, this sets its orientation to horizontal or set measure with largest child enabled true, while in vertical orientation, both cases make 2 passes for each child element. Grid layouts, they can end up making double traversals in the layout if they use weight distribution or Android layout gravity to any valid value. The cost of double taxation becomes a lot more severe the closer that view is to the root of the tree, because now you just, it gets a little exponential and it really slows down your rendering time. So the deeper the view hierarchy is, the longer it takes for input events to be processed and for views to be updated accordingly. Now I want to talk about this. So here's an example of an open source application. I think this is actually a reference to the one we talk about in the book a lot. And it's a pretty simplistic design, but you can see here this is a layout inspector. I think there's 3D rendering on this one, which is kind of fun. So you can literally see how deep the tree is. Yeah, so suppose a user clicks a button in an application, then the interaction must travel to the root view element before, you know, any of the source code processes. So for this reason, not only must we worry about view hierarchy complexity, but we also need to be mindful of using certain kind of views, you know, like the relative layout, linear layout, and grid layout. Okay. Bonus slides, because I think we got through everything. And I know all this memory leak stuff is pretty exciting, but it's a totally different conversation when you go back home to talk to your team about it. My co-writer has some very wise words. He's like, don't put in leak canary unless your team is ready for it. But actually, you know, there is a way to start this conversation with teammates because, you know, as I mentioned, memory leaks is kind of a humbling experience, especially when teammates find out they've been putting in memory leaks. So, you know, there's always kind of a kindness component. I mean, even the JetBrains guys and the Google guys, they've put in memory leaks too. It's something everyone does. But if you want to make this kind of a thing at your work, I find that it's possible to do this through grassroots movements. So, you know, you start the conversation with your teammates first, hey, you want to check this out? Then eventually you get some other teammates in, And for me, I found that the game really changed once I got QA in on it, because I just sat them down and I like told them very technically what memory leaks were. And like they just kind of ran with it. It was so crazy. Like they figured out, like they were able to figure out like what memory leaks looked like from like Firebase crashes. Like, hey, I'm not sure, but this kind of seems like a memory leak. Like even the ones where it was like symptomatic but not the cause. And I'm like, I was just really impressed. It was really crazy. So definitely involve your teammates. If you're able to involve QA, that's even better. Watch your analytics and record them. How many crashes are users experiencing in a 30-day period? You know, I'm sure people know, like, you know, we all wish we were able to get like more data permanently from Firebase, but we know that's not a thing. I feel like I should talk to those guys or something, because this would be really important. But what you can do right now is just kind of look at your 30-day, 90-day period, I guess, and take screenshots and just kind of keep track of it that way. If anyone has other ideas for tracking that stuff, I'm open to hearing more about it. But the point is, you want to be able to record what your work is actually doing, because, you know, it's kind of hard to sell to management, oh, performance is important. I mean, performance is important if you care about your user experience. But what I think like something that kind of like helps management be like, okay, we're kind of like on board with this, is to profile and record your application before and after the fixes. Record the startup times, the UI rendering and response times, memory and CPU consumption, and you know, if like QA is able to help out, maybe they can even track like, hey, like how many like crashes are we getting? Are we like getting more or are we getting like less users like dropping the app? You know, if we're able to like find any data like that, like that's the kind of the ammo that you need to be able to like have this conversation with management and essentially have them trust you to do your job. But yeah, I think that's everything that I kind of have. I'm gonna be out of social battery today, but tomorrow, I have like the editors sent me like some free copies for the book, so I'll just like sit out somewhere tomorrow morning in the conference and I'll give out signed books or something for free. So I don't know, it's also on Amazon and O'Reilly, so maybe just like wait to see if you get a free book and I don't know. But yeah, that's all I have for now. Thank you so much for coming to the talk.